Okay, this is a pin cast solution for the third exam, review problem number 5. Okay, in this problem, we're looking at a certain digital part. In fact, it's kind of an old part, and it has some worst case loading conditions specified as under the worst case high, the device would need to source 0.4 milliamps of current to drive the load that is hooked up to the device. How do I know it's sourcing? Because that's a minus sign, so the current would be coming out of the device. Okay, on the low side, when for this particular test, the worst case low is 0.5 volts, and the device would need to sink 12 milliamps to make that load work. So we can consider, this to be a limit for the amount of current that the device can sink. Okay, so we're supposed to take a look at different load conditions and determine whether or not the output drive specifications are exceeded. Okay, so you can think of the current specifications as being the litmus test. So we'll set up the problem to include the worst case output voltage conditions, check the current output under those conditions. Okay, so let's get started. In the first case, we're going to look at 910 connected to VCC and 1200 connected to ground. Okay, so let's draw that circuit. Okay, so we have a NAND gate, and it's connected to an output resistor that's 910 to VCC, and I needed to specify VCC in this problem. VCC is 5 volts. That needs to be part of the problem statement. Okay, and then between here and ground we have 1200 ohms. Okay, so the first thing you need to do is to be able to take a look at this part of the circuit and replace it with the Thevenin equivalent. Okay, and so what I want you to be able to do is just to go straight to that. Okay, so what we know is we're connecting to our Thevenin, and we want to know what that value is, and also V Thevenin, and we want to know what that value is. Okay, well, we've done this enough times where we really know the answer. Our Thevenin is going to be 910 in parallel with 1200. Okay, so you do that calculation and you get an equivalent R Thevenin of 518 ohms. Okay, and then over here for V Thevenin is just a voltage divider between the 1200 and 910 ohm resistors that are connected in series across this load. Okay, and so that would be 1200 times 5 volts, which is VCC, divided by 1200 plus 910. Okay, and so you do that calculation and you get V Thevenin is 2.84 volts. Okay. All right, so let me move this out of the way. Okay, so at this point, we need to check our loading conditions and there's a high state loading condition and a low state loading condition. Okay, so let's first take a look at the high state. Okay, and so what we would do is we realize what we need to put down. First of all, let me copy this so we can use it again in a second. Okay, what we need to put down is that this voltage is 2.7 volts under the worst case high conditions. Okay, so if this is 2.84 at this point, and this is 2.7 at this point, then the actual current goes into the device. And remember, on the output side, we don't have a limit on how much the device can sink. This current's going into the device, so it's sinking it. We have a limit on how much it can source. Okay, so because it's sinking and not sourcing, we're good, right? So the reason for that is V Thevenin minus VOH min is bigger than 0, which means we are sinking current. Therefore, everything's good. So for the high state, we're good. Okay, now let's worry about the low state. Okay, so low state, we take essentially the same circuit, but this time what are we going to do? We're going to put the worst case low on the output. So the worst case low, if you scroll up to the problem statement, is 0.5 volts. So 0.5 volts goes right here. Right? And so from that, we can see that the output current for the low state is going to be, under these conditions, bounded by 2.84 minus 0.5, right, the current going in. So I have this voltage minus this voltage divided by 518. Okay. And so when I calculate that, I get 4.52 milliamps, all right, which is less than 12 milliamps. So again, I'm good. All right, so I check the output and I check the input. So for part A, this load will work. Okay, so now we're finished with part A. Now let's do part B, and in part B we have 610 connected between the output and VCC. Okay, so you see, here's our circuit for part B. Let me start over. We have the AND gate. Okay, so that's essentially a Thevenin equivalent circuit. I could redraw that as 610. Okay, it looks like before. Okay. So we can check our conditions. All right, the high state, the worst this would be is 2.7, and our current would be, again, sinking, and so, which is good because we have a limit on how much you can source. You can only source 0.4 milliamps. So for the high state, you see that it's pretty clear to me that it's sinking because 5 volts is bigger than 2.7, which means the current is going to flow this way. It's going to be sinking, not sourcing. Okay, so for the high state, we're essentially good at this point. Okay, now let's look at the low state. It's the same circuit, but this is 0.5 volts. And this is 610 ohms. All right, so this is going to be sinking. All right, remember for low state we have a limit on how much you can sink. All right, so I output low is going to be 5 minus 0.5 divided by 610. So I can do that calculation. I get 7.4 milliamps, which is less than 12 milliamps. And so what that means is we're good. All right, so we checked both high state and low state, and so it looks like our conclusion is for part B. Again, yes. Okay. So finally, let's go to part C. And in part C, what we have is 510 connected between the output and ground. I'm sorry, 5100 connected between output and ground.